Good evening, everybody. Welcome to the Friends of the Libraries program, Beyond the Shadow of a Doubt, What's Going On During a Solar Eclipse. I'm Janet Vogel, I'm the Library Director. Before I introduce our wonderful speaker, I have a few housekeeping notes for everybody. So I will moderate the audience questions from inside the room and on Zoom so that everyone can hear, so we will force you to speak into the microphone. All of our Zoom attendees are muted and can only chat questions to me. You can't chat with one another. You can also submit Q&A, so feel free to submit any questions that you have along the way. Also, please do save the date for our Friends of the Library book sale, which is March 21st through 25th. I've got flyers up there. The last 2 days, Sunday and Monday, are bag days. Bags are provided, and they are $5 on Sunday and $1 on Monday. And the Friends of the Library's annual meeting will be May 8th at 3 p.m. And of course, the Friends are also co-sponsors of the Hiram College Solar Eclipse event on April 8th, one of the reasons that we're doing this program. So to learn more about that, you can visit hiram.edu and click on events. And of course, for our Friends of the Library events, you can visit the library's website, library.hiram.edu. And the library is also sponsoring a number of events this semester as a part of a grant we received from the State Library of Ohio, including one next week about using artificial intelligence to help you select the next book you might want to read. So that's on Thursday, the 29th at noon. So check that out. We will probably offer another one of those because I think that might be an interesting, popular one. And again, the library's website is the place to go for that, and that event will be hybrid as well. And of course, thank you to the Friends of the Library members who sponsor these events. And if you would like to join the Friends of the Library and support events like this, as well as the purchase of books and other materials, as well as building improvements, so this room was renovated in part thanks to the Friends of the Library, please speak with me after the session, or we do have some forms up at the front as well. Or you can visit library.hiram.edu and click on Support the Library. And now the reason that we're here, of course, is to hear from Daniel Gavazzi. He's a 2010 graduate of Hiram College with a degree in physics and a minor in math. Gavazzi then went on to earn a master's in physics from Kent State University. He will complete his PhD in biophysics from Kent State University this summer. Daniel's research focuses on protein folding. So he uses computer models to simulate protein folding, which has led him to teach both computer science and physics here at Hiram College, and also to teach at Kent State University. So thank you, Daniel, for taking the time to speak with us this evening about the solar eclipse. We're very excited.
Thank you. Hopefully everybody can hear me. As my students will tell you, I tend to talk fast, but I'll try to keep it a little bit slower. Luckily, we do have some subtitles going on. So today we are dealing with shadows, hence on the shadow of a doubt, and mostly the shadow of the moon cast on the Earth, known as an eclipse. Now, a little bit of introduction. The word eclipse comes from Greek, eclipsis, meaning disappearance or, more importantly, abandonment. So there are views of the sky back in the day, early models of astronomy that we dealt with where everything revolved around the Earth. There are a lot of celestial sphere moments where we have our zodiac, the sun would go around, disappear, and we were very localized, as you know. People felt the Earth was flat, and we didn't move around too much. So if something happened locally, it might have been the end of the world or the new beginning. So this abandonment basically is how they felt. The nice thing about eclipses is we understand them much better today than we did in the past, of course, and we can predict them very accurately. We have great models. We can even go back in the past, which is great for historians and archaeologists that find old ancient documents from ancient cultures referring to these great events where it turned to night during the day, and of course they felt that they were being abandoned by the gods, but in general it's an eclipse. And because of our modeling, we can then date those documents and find out when these key events actually happened and use them to find out chronologically when events occurred. So today we see eclipses much differently than we did in the past. of course, they are still rare and yet common at the same time. And that's kind of what I'm going to talk about today. First, we're going to talk about why eclipses happen, and then move on with our limited time as to what we still study during an eclipse and why they're important. So these pictures that you'll see, most of them come from NASA. The very first picture I had here is where we can see the corona of the sun around the moon during an eclipse. And hopefully you'll be able to see that because this is for a total eclipse. And we're lucky enough to have that in our area this year. So why do we have eclipses? And it basically comes down to math. It's an angular size situation. If you think about the sun, it is a huge ball in the middle of our solar system. And it's really tough to block out a giant object. But luckily, because of how distances are, it's basically a forced perspective. So you can block a whole mountain out of your view if you put a box in front of your face, that type of situation. So if we don't think about it as sizes and distances, but what's called an angular size, then we can see why eclipses can occur. Now, an angular size is basically an arc length. If you think of a giant circle, we can think about this angle as being our theta there, as we have marked here in our diagram. The distance d, the object is away from us, and this height. And we can see that this projection of this three-dimensional world is kind of on a two-dimensional plane that we would see, almost as if you were taking a picture. Now, what's great is if you do this calculation for our angle, our angular size theta there, you'll see that the sun's angular size will range from 524 degrees to about 0.542 degrees. Now, I know Mark's probably angry at me because I'm saying it in degrees instead of radians, but you can convert if you wanted to. If we do the same calculation for the moon, we also get a range of around 0.49 degrees to about 0.587 degrees. Now you can see that those ranges overlap, which means at times, as forced by our perspective here on Earth, the size of the moon and the size of the sun can actually be the same. Sometimes you'll see the moon smaller than the sun, sometimes larger than the sun, depending on where we are. But for the most part, this is the reason why the moon, a small object smaller than the Earth, can block out a giant object such as the sun. Now, this calculation, you do need to know the distance you are from the Earth to the moon, from the Earth to the sun. But luckily, we had a lot of mathematicians and astronomers in the past that have made all these calculations possible, so we don't have to. And I just wanted to get some equations out of the way because astronomy is a physics physics topic, which means we need to have some math. The rest is all going to be kind of views. So that's one reason why we're actually able to see this. The other reason would be their positioning. And we'll talk about the orbits in a little bit. But going back to that angular size, if we do some ray tracing, so if we assume that light is basically traveling in a straight line, we can see where the shadow will be cast. Now, much like me with multiple light sources around, I'm casting multiple shadows behind me depending on where this light is coming from. And you'll see where those shadows overlap, just like on stage, you'll see a much darker area. So if we trace the left side of the sun past the left side of the moon, the right side of the sun past the right side of the moon, you can see how there's an area that we have a very dark circle. That is called the umbra. Now, if that part of the shadow falls on Earth, that's where you will have a total eclipse. The other spot, you can kind of see how the left side, if we trace it to the right side of the moon, we can see a little bit more of a shadow. Think of it as kind of two spotlights. Now, that means that some of the sun can peek out in those areas. That is the penumbra. So that lighter gray in this diagram would be kind of the lighter shadow part on the figure on the right. Now, that's where you would get the partial eclipse. And there's one more that's not quite the umbra, which I'll show you in the next slide. But all of this is dependent on these orbitals. And our moon does not orbit perfectly circular around us, neither does our Earth around the sun. They're very close to circles, but sometimes we're closer, sometimes we're further. So you can imagine that these angles will change depending on where we are in our orbit. So whenever we're close enough to the moon, such that the sun is blocked out entirely, again, if we look at those angular sizes that I mentioned before, this is when the moon is large enough to actually block out the sun because of the distances. We can have the umbra, which is where we have our total eclipse. And then we can have the penumbra, which is kind of the outer areas, those partial eclipses. But if the Earth is further away and the moon's angular size is actually smaller than that of the sun, we have our third, the antumbra. Now this is an annular eclipse, which is the third type of eclipse that you might have heard about. So most of the time when you hear the news, they're talking about total eclipses and annular eclipses. And these actually happen quite a bit around the world, but as you'll see with my talk, it's kind of a big deal when it happens in Ohio. The second reason that these eclipses happen is because of the orbitals. Now we do have the moon orbiting around the Earth, and we have the Earth orbiting around the sun. And this type of blasphemy with the orbit around the sun happened that Galileo was put under house arrest by the Catholic Church and finally pardoned in 1990s. But better late than never, I guess. There's plenty of proof that the Earth does orbit around the sun in our solar system. However, technically, because the universe is infinite, the center of the universe is wherever you want it to be. So as long as you claim that first, you're the center of the universe. Now, none of this is to scale, as you can imagine. The sun would be much larger and the moon would be much smaller than the Earth. But I like this diagram on the left that NASA created, where we have the phases of the moon. So the outer ring here would be the moon as we see it from Earth. And I have the sun placed on the right here just to remind us that that's where the light illuminating the moon that we can actually see the moon from is coming from. So when we have our new moon, that is actually when the moon is out during the day. And the sun is just so bright that we get so much scattering off the sky, that it just is blue and we don't get to see the moon. Not to mention the moon would be extremely dark because the only light source to light it up is from the sun, and it's on the opposite side. Then we have our waxing phases. That's when the moon seems to be growing, starting with the crescent, going through the first quarter, then the gibbous. The gibbous is where it's a little bit past the half. You have that slight rounding on the other side. And then we have the full moon. So the full moon is when the moon is on the opposite side of the Earth. So the new moon and the full moon are the two times that we can actually have an eclipse. When we have the Earth and the sun sandwiching the moon, so our new moon phase there, that's when we can have a solar eclipse, because the moon is out during the day. However, the full moon, that's when the moon's out, and at the highest point at midnight, that's when we can have our lunar eclipse. That's when the Earth casts its shadow on the moon. And that also has a lot of special measurements, so you can measure the radius of the Earth from that. You can prove that the Earth is actually round and not flat. But again, we're talking about the solar eclipses today, not those lunar eclipses. So we have this moon orbiting the Earth, and then we have the Earth orbiting the sun. And what's unique about this, and this is why these eclipses are common but also rare, because we have these cycles once a month with the moon, and we circle the sun and we rotate every day, but the orbits of the moon and the sun, they're slightly at an angle to each other. So if we were to look at the plane where the Earth is circling the sun, and think of that as being a flat sheet of paper with the sun at the center, and we just drew a circle as to where the Earth is going. And then the same style where we have a piece of paper showing how the moon goes around Earth with Earth at the center, you'll see that there's a slight angle between the two. It's actually a 5-degree tilt. So there's actually only 2 times a year that we're lined up perfectly to be able to get eclipses. These are referred to as eclipse seasons. So we can see at the top and the bottom of this diagram, the plane that the moon is traveling in actually intersects with the plane that the Earth is traveling in as it goes around the sun. when we have our new moon and our full moon phases. Again, those are the two phases of the moon that we're actually permitted to have eclipses. On the sides, the right and the left, because of that slight 5 degrees tilt in the moon's orbit around Earth, well, the moon's either too high or too low to actually get those eclipses. So we either see it in fall or spring, but it slowly rotates because although we have 365 days in a year, that's from our reference point. If we were looking at Earth going around the sun from the stars, you would see that it's not exactly 365 days. We're off by about 0.24 of a day, which is why we have fun years like this year called a leap year, where every 4 years we have to make up a day. And there's special rules because it's not exactly 0.25, it's 0.24. Every 100 years we made up too many leap years, so we have to ignore that, but every 400 years we have to make it up again. There's a lot of rules with leap years, but that's because we chose to use the sun and where it returns in the celestial sphere. Again, that's our sky, as opposed to where Earth returns to the orbit. And there's some benefits to that. We lock in our seasons when we do that. However, we would be able to lock in some of these eclipse events if we did the sidereal year, which is how Earth revolves around the sun as viewed from the stars. So these are the main two reasons that we actually can predict eclipses, because these are the two causes of our eclipses. Number one, we have the same angular sides. So we can actually figure out, based on that ray tracing I was talking about, what the angular size of the moon and sun will look like. So we kind of know what area is going to be affected. We know that Earth makes one revolution on its axis every 24 hours. We know roughly 365 days around the sun and roughly a month for the moon to go around us. So we can make nice computational models that can simulate all of this. And we can base it on the past, present, and predict the future for all these eclipses. And if you go to NASA, they have these maps. So these are wonderful eclipse maps. Now this one is the annular and hybrid solar eclipses. I didn't really talk about hybrid, that's kind of the mix between annular and total. As you saw, we have the umbra, and then that turns into that anumbra. And there's kind of that fine point just in the middle between the transition that you kind of get this hybrid. So here in red are all these annular ones, and this is from 2001 to 2025. And I know you guys aren't thinking that that's too special because it's 2024. Looks like it's only a one-year prediction, but this was posted back in 2002. So they predicted 23 years worth of eclipses. And those are the annular ones. So they knew, based on the distance the Earth is going to be away from the sun and the moon, that these would be annular eclipses as opposed to total eclipses. We can also look at the total solar eclipses. Those were also predicted. And we see that there's a lot happening, that if you had a lot of money, you could travel the world and see so many eclipses in 10 years. And if you owned your own yacht, you could also see a lot more eclipses. So although these are very common, we have eclipses basically twice a year, it's just not going to be in our area. So it was a huge impact on all those ancient cultures because they weren't mobile. They couldn't jump on a plane and go eclipse touring like it's a Taylor Swift concert, but they were localized, which means there's a huge gap between when they're going to see it and when their next generation is going to see it. In fact, if we trace this back, first of all, just a reminder, here's our April 8th, 2024 eclipse path. We see all of Ohio, well, half of Ohio is in a total eclipse, all of Lake Erie is, and the other half would be in that penumbra, so partial eclipse. So there's going to be quite a bit of viewing parties, I'm sure. But going in the past, here is 1981 to 2000 predictions. We can see that the last eclipse Ohio had is right here, and that was an annular eclipse. It's one of those where it's not a total eclipse because the moon was slightly smaller than the sun, but we had an eclipse. The last total eclipse, we have to go even further back in time to the 1800s, where we can see here in 1806, in June, we had a nice total eclipse. And pretty nearby, we also had in 1811 an annular eclipse. Well, that's great. We know that they can predict at least 20 years. But what's really fun is with this modeling and with our computers, we can actually figure out when our next eclipse is going to be. And again, if you go to NASA and just look at these eclipse calendars, eclipse maps, they have so many different decades and centuries that you can look at. So here's the one from 2081 to 2100. And we can see that the next big event in Ohio is going to be roughly in the year 2099. So that's the next total eclipse. We have another annular eclipse in 2093, which I'm probably not going to be around for, but it's good to know that that's the next time it's going to be in Ohio. So grandkids, great-grandkids, next generations will be able to see it. But we see that these eclipses are rare if you never left Northeast Ohio. I mean, it was about 200 years before between the last total eclipse and this current one. And it's going to be almost 100 years between this one and the next one. But luckily with our modeling, we can figure it out. Now, it does get a little sketchy when we look into the 2200s. But again, there are some things that we can easily compute, and then some things that, that's quite a bit into the future there, that we're not 100% certain if that's going to be true, so we just need to keep and make sure things are updated with these predictive models. But this is why the news keeps on talking about, oh, this is a huge event. It's the only total eclipse that you'll be able to see in your lifetime if you stay in Northeast Ohio. But again, you're permitted to move around the world if you have enough money. So basically, that's why these eclipses occur, how often they occur, and why we know when they're going to occur. But the question is, why do we care? Other than it's a really cool event that you can say, I was in Northeast Ohio when we had a total eclipse. Well, there's a couple of studies that can be done, and still more other than that. Like I said, with the lunar eclipse, you can measure the radius of the Earth. You can see the curvature of the Earth. But with a solar eclipse, it helps us study the sun. And the reason why we want to study the sun is because everything in this universe that we are trying to predict, to understand, is based on what we can actually measure, and it takes a long time to get out of our solar system. So the only star we can truly study is the sun that is easy enough to make these measurements. Everything else is so far away. And to make these measurements and studies of stars, which is what our sun is, we rely on phenomena dealing with light. Now again, I'm not going to bore you too much with a lot of the specificities. I know that there's a couple people here that are like, oh, I wanted to hear the nitty-gritty on spectral lines, how intensity dies off as 1 over r squared, Doppler shifts, but they are very important. So I'll give you a brief summary as to why these are important. Number one, these spectral lines tell us the composition of stars. As a gas burns, it releases basically a fingerprint. And these are from hot gases burning. And if you're going to be doing physics too, or anything along those lines, you'll be able to look at these spectrums where there's specific lines because of the electrons getting excited in there, and then just having a sugar crash and wanting to relax, and all that energy is released into the universe in the form of a light. And we can look at those colors and understand, hey, that's helium there, or that's hydrogen there. And we can actually see what the building blocks of these stars are. We can also see that as light passes through a gas, that gas is going to absorb some of that spectrum. And we can see what is made up in that gas as well, and what elements are in there based on what it absorbs. So these spectrums are very important as to knowing what the composition of our universe is. Intensity helps us determine distances. Like I said, intensity, so think about a candle at the end of a dark hallway. If you're next to it, it's nice and bright, but as you walk away, it gets darker and darker. How bright that light is dependent on how far you are away from that light. So we can measure intensity of these stars to help determine a distance. Something that I forgot to put on there, black body radiation. It's also a big thing. It tells us temperatures of things. Doppler shifts. So Doppler radar, everybody's heard of, or everybody's been caught at Hiram trying to enter, and you have a police officer with a radar gun there. So it helps you determine direction and speeds of objects. So this allows us to determine how things are orbiting, spins, and even with the sun, there's certain layers of that sun where there's fluid going down as fluid's going up, and we can determine how that is rotating in the sun to help develop our models of the sun. And again, that development of the model of the sun helps us develop the model of the universe and everything that we know of the measurements. So that's why taking these measurements very carefully is important. But one problem with the sun is it is very bright. I'm not going to recommend looking at it anytime soon, especially without anything protective over your eyes, but it's extremely bright. And the main part that we see is called the photosphere. That photosphere is this thin layer right here. So we basically have the core of the sun, that's where all this nuclear reaction's going on. This radiation level that's emitting more radiation as it absorbs heat and energy from the nuclear core. We have this convection zone that's basically rotating the inner core. Hot rises, cold settles back down, and it's helped pulling out all of that from the center of the sun outward. And then you finally have this photosphere that's extremely bright. So that's what we can easily measure, but it's so bright that the layers above that, we have the chromosphere, the transition zone, and the corona, basically the atmosphere of the sun. It's kind of like you're trying to do a lab experiment or develop film and somebody has a flashlight right next to you and they're just ruining all your measurements. So we can't really measure anything dealing with the sun's atmosphere while it's on. And there's no real off switch for the sun. So we have to wait until a moon passes in front of the sun to block out all of this photosphere light coming at us, such that we can actually make those sensitive light measurements to determine what the atmosphere of the sun is. We can see some cool solar flares, and that first picture I showed you, we can't get because that's the corona. The photosphere is so bright that you can't even see that when trying to measure that. You need very sensitive equipment and special filters. So basically, we need these total lunar eclipses to be able to further develop our theory on the sun. And that is part of the scientific method. Where the scientific method is basically you have a natural phenomenon, you make a theory to test it, but you have to continually test it. You have to continually grab data and analyze that data to see if your theory still holds up. And if your theory doesn't hold up, you need to tweak it. You need to either add a correction to it or come up with a new theory that helps accompany everything else. One theory, which is going to throw everybody off, is general relativity. Now, I know a lot of people know this kind of guy called Einstein. He's kind of famous. He more or less moved physics into the modern world that he has created two main things, special relativity and general relativity, along with a lot of other contributions, but these are the ones that he's most known for. And he was a guru at coming up with thought experiments. And all of these basically revolve around the principle of equivalence, meaning if you're making a measurement in this room, and you make it in the next room, the physics better be the same between the two rooms. So when he did special relativity, it was a thought experiment about non-accelerating frames. So think about being on a train going at a constant speed. If you were to do physics experiments on that train, it should be the same result as if you were doing your experiment on the ground. Well, this one is a little bit unique. This is an accelerating frame. So imagine you're stuck in the elevator here. I don't think many people want to imagine that, but imagine you're stuck in the elevator here at the library. And you feel that you have some accelerator pulling you down, that's your weight. And then, basically, you don't really know if that elevator is still here on Earth, or if that elevator is in outer space with no gravity around and it's just accelerating as if you were feeling Earth's gravitational acceleration here. So because of that, both of these two frames should be equivalent. If you do physics in one, it has the same as if you're doing physics in the other. They both have gravitational acceleration, pulling your experiment down to the bottom of that elevator. Well, it gets a little bit weird when you introduce light. Because imagine there's a hole in the side of that elevator, and here, well, the elevator's not moving. You feel regular weight as gravity's pulling you down. Somebody shines light through a hole of that elevator, and it just goes to the other side of the elevator. Well, on the other one, the elevator's going up. Well, where that light was aiming, technically drifts down a little bit because the wall has moved up. We have a slight contradiction. The only way that these two can be equivalent is if gravity is actually bending space, which is a really weird view. So imagine kind of this weird hockey table here, where we have a rock in the center of it. Well, that rock's small gravitational field, because if you have some sort of mass, it has a gravitational field around it, is distorting the space around it. So it's no longer a nice flat two-dimension. You can imagine that the space kind of bulges downward at that point. So that if you were to have a ball get shot towards the rock, it would kind of wrap around, not because of the gravitational field of the rock, but because of how the space is curved around the rock. Now that's just a fun little cartoon, so is this. But if we look at the sun's gravity is 274 meters per second squared. Now I know you have nothing to reference that to. Earth's gravity is 9.8 meters per second squared. So the sun has 28 times Earth's gravity. And although this is an acceleration, that basically deals with your weight, which is a force. So everybody would have the same mass in both areas, but the acceleration pulling us down means that if we stand on a scale, it's going to have two different readings. Put it in perspective, if you were to take a 5-pound dumbbell from the rec center down here at Hiram, and then take it to the sun with proper heat protection, that 5-pound dumbbell has just become 140 pounds. So it got really heavy all of a sudden. And that's because Earth has such a great gravitational field around it, which means with special relativity, the space around Earth, the sun, is going to bend. Now, as you saw earlier, I had light drawn in straight lines, which is great for cartoons, but technically light doesn't travel in a straight line, it travels the shortest distance. And in our usual Euclidean geometry, where we have a nice grid, where you would have a nice square for each spot, that is a straight line between these 2 points. However, if space is bent, as we see here, it might be shorter to go around the pit than to go down in through the pit. So you actually can observe this during a total eclipse, where that sun's gravitational field will allow stars that are actually behind the sun, so a straight line between Earth and that star will go straight through the sun. It actually will bend around the sun. And you can see it as if it's appearing to the left of the sun. So this, you might wonder, how the heck can we figure this out? Number one, we need it to be nighttime while the sun's out, only done during a total eclipse. Number two, we have to take a picture that can actually see the stars and be extremely patient. Because the only time we're going to see that sky at night again is 6 months later when we're on the other side of the sun. So that way we're facing the same section on the celestial sphere, as they would describe it, that we did when the sun had a total eclipse. And you can match up and line up the stars that did not undergo general relativity and just find out which stars did undergo special relativity. Sorry, general relativity. So, and you might wonder if that's kind of the only scenario that we see this, and it's not. We've actually had some other general relativity advancements in our lifetime. We have basically two giant laser beams that are in sync, 90 degrees, and they send a pulse down a mile track, extremely level, making sure that they account for Earth's curvature with everything, and are perfectly level. And whenever two giant objects collide in the universe, they send out a gravitational wave. And that gravitational wave, that anomaly, will distort space. And if the experiment was set up right, you'll see one of those beams gets a little bit shorter than the other. And we can measure that based on our light was in phase. If there's any change in that, it's going to be out of phase. And we can make these measurements and actually see that that's true. Luckily, I believe it was two neutrino stars colliding about 10 years ago maybe, that we got to see this happen. And it was confirmed by two different stations. So this general relativity and these gravitational waves distorting space is a thing. We also need to worry about gravity's effect on time, because satellite dishes that we rely on so much, their clock would be a little bit off because they have less gravity acting on them. But I won't go into that because it doesn't quite deal with eclipses. So something that you guys are really interested in is, how can you view these eclipses? And the best way to view it is with nice, safe viewing filters, which I believe we have ordered if you are able to attend our eclipse event. But a lot of them will be available. I'm sure you can find them online, many other places. They even have ones that you can put on binoculars and telescopes if you wanted to get a closer view. But again, be very careful, of course, because you're still looking directly at the sun. And if you grabbed a brand that was not officially tested, it could cause eye damage. So don't look directly at the sun. I don't know how many times I want to tell you that. I kind of want the picture of Trump looking directly at the sun at the last eclipse. Yes. If you don't have a solar filter, it's okay. You can use a colander. So this is somebody holding up a colander during the eclipse, and you can see all of these crescent shapes. That's actually the sun as the moon is passing in front of it. You won't be able to see an amazing picture like the corona that I showed you at the beginning, but you can watch the eclipse happen. Or you can use a tree. As light passes through the gaps between the leaves, it's just like the colander. Basically, you'll notice if you just have something with a hole, you can watch the eclipse happen. So this is using your hands if you basically make a mesh, making little holes between your fingers. Which leads us to the most common one, the pinhole camera. Now, pinhole camera is fairly simple when it comes down to it. You just take a piece of foil, put a little hole in it. This one on the left is them projecting it onto a piece of paper, and then you can watch it just like I showed you with the tree, the colander, and your hands. Or you can put it in a box. So if you put it in the box, put a nice white piece of paper on the other side, and then make yourself a little viewing window. So that's going to be nice and dark in there. And also, it has the added benefit of you looking away from the sun as you're looking at the sun. But these are great, and I have a video later as to pinhole cameras and making a cool room from a pinhole camera. But in general, what's happening is most holes, you won't be able to get a nice focus of an object that you're looking at, because they're so large that light is coming off of this in every possible direction, that as the light adds up, when you have the presence of all light, it turns white. So basically, it's just natural white. As you close the surface that light is passing through, so that's a small hole, well then very little light can go through. So there's a lot less interference, a lot less of this bright white spot. And you end up with an inverted image of the object, where if you trace the line from the top going down, and then the bottom of the tree going up, you can see that it's inverted, and that's in general. Now, you don't have to take my word on it. I do have a National Geographic's video I'm going to show you here in a little bit. Hopefully, Zoom permits me to broadcast it through, but that is the pinhole camera. If you have a refracting telescope, you need to be careful, but there is a way to actually project it with a refracting telescope as well. Now, it's recommended to make a nice collar. So what you do is you just get cardboard, you put it around the telescope so that it will cast a shadow to what you're projecting on. And then you point it at the sun. Again, do not use the viewfinder when pointing it at the sun. It is a bad idea. But it will focus the light using lenses as opposed to that pinhole, and you will be able to see it projected. Again, be careful with this method as well, because as we know with magnifying glasses, you can cause fires. So this does have a slight burn risk. And of all the ways, do not look directly into the sun. I think I've said that a few times. Now, before I go to questions, I do want to, let's see if it will allow me. Oh, I'll exit like this. And I have to re-hide all the tools up here. So many things in the way. All right. So like I said, I have a little National Geographics. And it's not the words of the music that's important for this, it's mostly what they're doing. So again, that pinhole camera needs to be in a very dark room. So they are taking tarp, placing it over the windows, and sealing it up as nice as possible so that they can cut a tiny hole in the window.
Camera obscure is
and it projects the outside into the room. And as you can see, it's inverted.
Looking out into the world.
So this is basically how the pinhole camera works. And if you wanted to and ruin a tent, you can make one of these outdoors to view the eclipse.
It's a very
It would actually be kind of fun if we had a window with the proper angle in here to do as well. But yeah, so all you need is some gaffer's tape, an X-Acto knife, and lots of tarp. And then you just cut a little dime-sized hole in the tarp, and you have a room that is just a large pinhole camera. And you can spy on people on the outside without them knowing. But yeah. So, that is one of the most common ways to view the eclipse. All right. And we can open it up to questions now. Yes. Yeah, we have to wait on
thank you so much, Dan. And we do have a printout of the instructions for making a pinhole camera up at the front.
So you said, it seemed like that you said that there are some problems with predicting the eclipses for the future. Can you go into why that is? If everything is predictable and static, what would the problems be with those predictions?
So with all these models, basically you have to use your last calculation to get your next calculation. So as time goes on, you can imagine 100 years that calculation might be good, but then you might have a floating point error. And that will propagate as time goes on. And who knows, maybe our moon gets hit with an asteroid. That's going to affect it as well. So there's a lot of little things that could happen as time goes on that would affect that. And that's why things get a little bit different as time goes on. And you have to, every so often, just recalibrate and double check your calculations. Any other questions? Yes, up here. Here comes a microphone.
I know this isn't a physics question, but what is the weather going to be like?
It's not going to be sunny because it's nighttime, but that's all I got. No, so in April, luckily it's Northeast Ohio, so partly cloudy, chance of rain. But it's like 50-50 chance of clouds.
It's a little training in the dark.
Yes. Mhm.
One of your early slides showed that when the angle is right during the spring and the fall, that that's when you're most likely to see the eclipses. But a later slide showed eclipses in June and in January.
Right, like I said, this is based on the sidereal year, which does not lock into seasons. So the seasons will slowly shift as you go. Right now, again, it's that 0.24 days difference between the solar year and the sidereal year. And that's why you'll see the months change. Because with the solar year, we've locked in the seasons and the months, but we didn't lock in these events. So hopefully that answers that. It does, but it does add up, especially because we add a day to February every 4 years, and then, anyway.
So we have a couple of questions online. One is, do I need to register in advance to attend the solar eclipse event on Hiram's campus? And the answer is it's not required, but we would like you to, so we have an idea of how many people are coming. And like I said, that is available on the college's website. I will put that in the chat for the folks here. And then, Dan, a question for you. When did people first understand an eclipse was occurring?
Well, they knew it was occurring when it happened, I would assume, but understanding what it was, that's a different question, and I'm not going to be able to talk about that without further research. So, unfortunately, but there are debates on whether or not an eclipse is recorded up to like 3000 some BC in some stuff that they found in Ireland. So, a long time ago, if that's when they are referring to just the moon's blocking out the sun. But you have to admit, it is kind of scary back then because the moon's invisible at that time. So it just kind of, sun disappears.
Yeah. And is it better to view the eclipse from the center of totality or a bit to the edge?
Well, it depends on what you like, I would say. So if you're kind of on the edge, you'll be able to see a little bit of the sun poking out. It might also depend on what you want to measure, but if you wanted to kind of possibly get a view similar to the opening slide, I would probably be at the center of totality there, just because you know that the moon is blocking out the sun evenly in all directions.
Hi, Daniel, big fan. So I have two questions. One, if you were talking about how on the sun, gravity weighs like 28 times more.
Mm-hmm.
So hypothetically, if I were to get the right thermal equipment, could I walk on the sun?
No.
I'll keep that in mind, I'm not gonna go there. And also, you said that this doesn't happen often in Ohio, so have you personally seen a total eclipse report?
No, I actually haven't. I was close to because of a summer school in Indiana back in 2017. So the last one that went through, that would be right here. So you can see this crisscross. So August of 2017, that was the last total eclipse that went through. I unfortunately was in Kent, Ohio at the time. So we only had the partial eclipse. So.
This year what is the apparent size of the moon going to be against the sun?
I'm not 100% certain, but it's going to be enough that we will have an umbra to get the total eclipse. So.
This might be stupid again, but so it doesn't matter if it's raining, it'll still get dark.
It will still get dark, yes.
Okay, because
It would just look like it's raining at night.
Okay. And then my other question is that beautiful photo, would you need a really special, amazing lens to get that?
So with this one, hopefully, what we're going to try to do, so this is actually, whenever you see photos like this from NASA, it's not quite fake color, but the colors do represent different spectrum of light. So this does have some X-ray color tossed in there as well. That one you do need a special telescope to be able to capture that. And that has to be above the atmosphere, so we do not have that technology here at Hiram, unfortunately. But you would be able to see kind of the white around it if you had a solar lens properly and like a telescope or a binocular.
Thanks for doing this. I feel capable of understanding this because you're explaining it very well. So I have a son who's a coaster enthusiast, and he collects like which roller coasters he's been on. Are there people who are eclipse enthusiasts who really do, with money, travel around the world trying to like check off eclipses?
I'm sure there are. I mean, there's probably a Guinness record that you would only be the one that could hold if you did that your entire life because of how vast these are apart. So if you wanted to be in a record book, I'm sure you could tell Guinness, I'm going to do that, and then try.
I do know that there was an alum in here this afternoon, and he said he'll have people staying at his house, and people have already like planned to park an RV in his yard so that they can be here. So I do think there are people who travel around for it. And we have a question here. What is the exact length of time that the eclipse will be seen? I read it will be 3 minutes and 56 seconds, but a simulation of the eclipse took about 3 hours.
So the total eclipse, I don't think lasts too long, but you'll get partial eclipse leading up to that. So the whole event does take a while, but you have to remember we don't have that much daylight to begin with. So it is kind of limited to how the sun and Earth revolve.
They were estimating about totality is like 12 minutes or something. I think in articles I've read, they said totality is around 12 minutes, but the whole thing starts around 2 and ends around 4.
And that would also depend if you're kind of on the edge of totality or in the center of totality, I would say.
And somebody is asking, according to NASA, the moon is slowly moving away from Earth. In what ways would that impact eclipses in the far/distant future?
And again, that's another thing. So it's going to reduce the number of total eclipses. But as you can see right now, the large side of the moon would be the 0.57 degrees. So we have about 0.05 degrees to go before the moon can no longer block out the sun. But again, it's all in the timing at that point. So we would see a reduction in our total eclipses and an increase in the annular eclipses, because this moon would look like it's shrinking. All right, if there are no more questions, thank you guys for having me.
Yeah, thank you so much.
Oh, we got another question. Oh, yes.
I'm actually on Team 24 for Citizen Kate this year. Do you familiar with that?
Yeah.
It's a NASA program where citizen scientists track the movement of totality across the American continent. I'm on Team 24. There's about 40 stations right along totality, and we're photographing the eclipse through just totality with a Polaroid telescope and tracking the movement of the sun. And then when we all get done, all these images will add up. They'll stitch them all together to create about an hour-long movie of the sun. With that hour-long movie, they'll better be able to tell movement of jets and the solar wind.
Which is kind of what we see poking around here.
Yeah.
Like I said, that's why we need these eclipses to help this study. And that's why predicting these models is great. So.
All right, wonderful. Thank you, everybody, for coming. Please feel free to snap a picture of any of our flyers that are coming up, grab a copy of the flyleaf that runs the library newsletter, take a copy of the information about how to make an eclipse viewer. Feel free to complete a survey about your experience here today, and I hope everybody has a wonderful evening. Thank you so much.